Hey math fans, in the last video we took an in-depth look at a problem called the secretary problem. We're going to conclude this section with one more example, and then we're going to introduce a little bit about independence. So, let me just remind you that the formula to find the probability of an event can be written as the sum of conditional probabilities given k mutually exclusive events that we'll call B1 through Bk. Okay, so this is a pretty important formula. We're going to go ahead and use that on this problem. So, problem says, consider flipping a coin. We're going to play heads or tails. If you correctly guess it, you win $1. If you incorrectly guess it, then you lose $1. So if you start off with, say, X dollars, and somehow through this process of winning and losing, you want to earn exactly M dollars, and we want to know the probability that you end up with nothing. So the probability essentially that you lose. Well, clearly, this is going to depend on how much money you start with, right? If you start off with more money, that means that it can vary a little bit more before you end up with nothing. But let's go ahead and kind of work this through. So in order to use this formula successfully, it's pretty clear that we're going to go ahead and let A be the event where you end up with nothing. Now, in order to make this successful, we need a bunch of mutually exclusive events that we can form and generate conditional probabilities with. So it's not very clear exactly what mutually exclusive events will partition kind of the universal set, but I argue that maybe we can partition this into sets B1 and B2, where B1 is the event that you win the first game, and B2 is the event where you lose the first game. I don't think anyone's going to doubt that those two events are mutually exclusive, and that B1 and B2 make up all possible events. So every possible event can be broken up into either winning the first game or losing the first game. Okay, so we're going to go and do that. So B1 is going to be winning the first game or the first round, and B2 is going to be losing the first round. Right? So then we have that the probability of A occurring is just going to be the sum of probability of A given that B1 has occurred times the probability of B1 plus the probability of A given B2 times the probability that B2 has occurred. Now, thankfully, the probabilities of B1 and B2 are extremely easy. Right? These are both 1/2. You can even write that. So the probability of winning the first round, well, if you flip a coin, it's either going to be heads or tails, and that's a 1 in 2 chance. Okay, so these are both 1/2. And I can go ahead and just factor that out. Probability of A given B1 plus the probability of A given B2. All right, now, as I said, clearly the probability of ending up with nothing kind of depends solely on how much money you start with. It doesn't really matter what the goal is, right? It doesn't matter that you want M dollars in the end, because as long as you have enough money that you start out with, it doesn't matter. Okay, so really what we can say is that the probability of A occurring, right, this probability of A occurring is a function of X. So what I'm going to go ahead and say is I'm going to rewrite this equation as not the probability of the event A, but I'm going to write it as a probability function that depends on the variable X. Nothing else. It's not going to depend on any other parameters. Okay? And we said that's equal to 1/2 of these two multiplied together. Okay? Well, what's the probability that A occurs given that B1 has occurred? Okay, so let me just kind of sketch out a picture. So this is u to start out with. And let's say, this is, winning the first round, and maybe this is losing the first round. So, given that B1 has occurred, you just won the first round. Okay, so what's the probability that A is going to happen? Well, if P of X is the probability that A occurs given an X value, where X is, of course, the amount of money that you start off with, at this point, you have X plus $1. So here you start off with X dollars, and here you have X plus $1. And the probability of A occurring is just going to be playing the same game, but starting off with X plus $1. Okay, so I guess really what I should say is we're going to go ahead and let P of A, we're going to define that as a function of X. And we're also going to let the probability of A, given that you just won, that's going to be the same as the probability depending on X plus 1. It's going to be a function not of X dollars, which is your starting amount, but at this point, your starting amount is actually X plus $1 since you just won. Okay, so hopefully you see where I'm going with this now. The probability of A given B sub 2, given that you just lost, is going to be how much? Well, at this point, how much money do you have? Well, your starting amount is going to be X minus $1. So really, this is the same probability function, but instead of depending on X dollars, you're really depending on X minus $1. Okay, so we should be able to write down kind of the function now. Okay, so we're going to go ahead and rewrite this. Okay, so we have that the probability of A occurring, which is P of X, is going to go ahead and equal 1/2 times P of X plus 1 plus P of X minus 1. Now, upon first glance, that looks like it doesn't help us at all, right? I mean, I just wrote a function, and we're trying to find that function in terms of two other functions that we're trying to find. Well, it turns out this is called a functional equation. And sometimes it's possible to solve these, sometimes it's not possible to solve these. A lot of YouTubers, do Math Olympiad style questions involving functional equations, and these are kind of entertaining to watch. Don't know why I said equational. But it turns out this one actually kind of has a pretty simple solution, which I'm going to get into in just a second. So this is the functional equation that we have to solve. P of X is equal to 1/2 P of X plus 1 plus P of X minus 1. So ideally, we would want some sort of explicit form where P of X is a function of only X. Okay, this is kind of defined somewhat recursively. Well, the first thing that you might notice is that this expression on the right-hand side is a little odd. Because doesn't this look a whole lot like an average? And in fact, it is. It's an average of P of X plus 1 and P of X minus 1. So let's just kind of sketch a graph. And of course, I don't know what P of X looks like. Maybe it's some sort of continuous polynomial, whatever. Okay, whatever. It doesn't really matter. And we'll call this P of X. And we'll let this be, X. And we'll let this be X minus 1. And we'll let this be X plus 1. And the idea is when you plug all those into the function, this value right here should be P of X minus 1. This value all the way up here, that should be P of X plus 1. And this, that's P of X. But what we're saying is that P of X should actually just be the average of this value and this value. So it needs to be directly right here, smack dab in the middle. Whoops, that does not look like in the middle. but that's where p of x needs to be. Okay, and if you'll notice, if p of x is smack dab in the middle between this point and this point, that really means that this should be linear. Okay, now it's not linear, especially in the case of this picture, but it should be, right? And that gives us our indication of what p of x should be. Okay, so we're going to go ahead and guess that p of x is linear. And of course, this isn't a proof. The proof that p of x is linear is actually very easy. If I'm going to go ahead and guess that p of x is linear, that means that I can write p of x in the form, y equals mx plus b. So in this case, we'll pick constants c1 and c0 to write this as c1x plus c0. Okay, and if that's true, then we need to make sure that p of x is really equal to 1/2 p of x plus 1 plus p of x minus 1. So the question is, do those two things equal each other if p of x is linear? Well, just plug it in, right? Okay, so this would be p of x plus 1 would be, it would be, let's see, it would be c1 times x. Okay, where in this case, instead of x, I'm replacing it with x plus 1. Okay, plus c0. Okay, plus p of x minus 1, which is going to be, if I plug that in, should be c1 times x minus 1 in parentheses, plus c0. Okay, so let's see if all of that checks out. And that is going to equal 1/2 of c1x plus c1 plus c0 plus c1x minus c1 plus c0, and then the c1s cancel. And then what do I have? Well, I have two c1x's, and I also have two c0s. So this is just equal to c1x plus c0, which was p of x. So I no longer need a question mark. This is true. Okay, so that's all you need to prove that p of x is linear. Now, figuring out why p of x is linear, that's what this whole graph was kind of designed to do. And really, this is a technique found in differential equations, where you just basically guess the solution based on, I don't know, magic or experience, and it just comes out to work. Okay, so now that p of x is linear, the only thing left to do is to find constants c1 and c0 using our boundary conditions. So we should know the probability of success, which, remember, was the probability of essentially getting to $0 and losing everything. Well, what's the probability of losing everything when you start off with $0? Because that's what x represents. Well, the probability of losing everything or getting to $0 if you start with $0 is 1. If you start off with $0, you're going to have $0 and then you can't play the game anymore. So that's going to imply that c1 times x plus c0 is equal to 1, which, since this is 0, is going to imply c0 is equal to 1. Okay, and the other condition that we know, because remember, we're going to keep playing until we get to m dollars. So what happens when you start with m dollars? What's the probability of losing everything and going to 0? Well, the probability of that is 0, because if you start off with m dollars, you've succeeded in your goal of getting M dollars and you're not going to play the game anymore, so it's impossible to lose all of it. Unless you're really bad at poker, or whatever the game was. Okay, so that's going to imply that C1 times M plus C0 is equal to 0, but we know that C0 is 1, right? We just solved for that, so I'm going to go ahead and replace that. Right. Okay, so now we just have to solve for C1. Well, C1 is going to be negative 1 over M. There we have it. So all in all, to answer your question, the probability function, which depends on the variable x, is going to equal C1x plus C0, which is minus 1 over m x plus 1, which I'm going to write in a slightly better way as 1 minus x over m. And even though it looks a little weird, this function is linear exactly as we predicted, and that's the answer to that question. Hopefully that was helpful. I'll see you in the next video where we talk about independence.